All right, so today lecture number 8 for DERs. I've mentioned this to some folks who are in class, but I think that we have been a little bit, or I have been kind of rushing to get through content over the last like roughly week. I went over on one lecture and then I've just kind of been scrambling to catch up ever since. And so that feels a little bit frantic. Also, you guys have been working hard on the homework. And so I think what we're going to do today is we're just going to kind of do a leisurely wrap up of the material from last lecture. So kind of the last section of the buildings part 2 slides. And then we will just have a discussion about just checking in, how things are going so far, if you have questions from the homework, stuff like that. And so I think we will stop recording after the lecture content, but then people who are on Zoom or in the room will just kind of continue with a discussion. And when we run out of questions or topics to discuss, we'll just break. So probably today's class will be a little bit shorter. And then where we're going from here, so we are moving right along in the first unit, the kind of modeling and simulation unit. So seems like ancient history now, but you may remember we had kind of a week of eating our veg durables, learning about linear ODEs, and see what I did there, and dynamical systems. After the first week where it was just a lot of kind of background about energy and electricity and so forth. And since then, we have learned about batteries and EVs and thermal modeling of buildings. And today, actually, we'll talk about kind of ways in which you can view a building as kind of like a battery if you squint and draw a mathematical analogy. And then we have heating and cooling equipment, so heat pumps, resistance heating, air conditioners, things like that. Then we will do a lecture next week on thermal energy storage, including water heaters, but also things like ice storage and other thermal storage media. Then we'll do a lecture on solar, focus mainly on sort of solar photovoltaics, but we'll talk a little bit about other aspects of solar energy as well. And then we have 2 guest lectures, each of which will have about half of the class to discuss. And that'll be on February 20th. And then we will do project presentations the following week. So these are basically, I think I mentioned this last time, but these are pretty much just pitches. Here's our idea. Here's a little bit of about what someone else has done that's interesting. And here's what we think kind of our secret sauce will be. Yes.
Is the solar homework 5 the last of like this weekly homework, or is there just like a break for a week and then like so it seems like the homework calendar changes.
Yeah, so the homework calendar changes, and homework 5 is the last homework from the kind of modeling portion of the class. And so that marks when we're going to stop the sort of weekly homeworks coming at you quickly, and then it'll slow down a lot. So we'll wrap up after the project pitches with kind of a summary lecture on the modeling content. And then this will mark basically the shift to the second unit, which is kind of about optimization and control. But then, yeah, after this lecture, basically solar homework, we turn that in. Then you have a week off to study for the midterm. And then after the break, probably we will only have 2 or maybe just 1 homework assignments. So that really in the second half of the class, kind of post-spring break, you guys are mainly focusing on your final projects. And the topics here are a little bit, a little up in the air. I still need to prepare these lectures, so we'll see what I put together. Does that address your question? Yeah. Okay. So one question came up before class, which is, are the solutions for the homeworks posted anywhere? And the answer to that is no. And the reason for that is that making good homework problems takes a while. And so I would like to be able to recycle homework problems, not every problem and every assignment, but some problems from year to year. And I feel like to a student, the value of the homework is like the real learning value of the homework is when you get stuck on things or do things wrong, and then you have to figure out where your mistakes are, right? That's really the learning opportunity. So if I posted solutions from last year, you guys could, not everybody would, but everybody could just find them and kind of, do the homework with a solution in front of you. And then I think that really takes away a lot of the learning in the experience. So that being said, many of you will get many of the problems completely correct. When the grades go up on Gradescope, you'll have full points, and that's fine. If you're confident that you did it correctly, you can kind of leave it at that. But if you get points off for something, then I think it's a good idea to go into office hours, either with me or with the TA, and we have the solutions for everything. So we will, and we're happy to show you kind of, in the moment, we'll show you a solution and you can figure out, oh, this was the bug in my code or whatever. And I do recommend doing that for the problems that you don't feel like you got completely correct, because that content can all show up again on the midterm exam. Okay. So does that sound fair? Yes.
With it being like if you get really close to the correct answer, then you get full points.
Yeah.
How will we know if we've got like a little thing in there?
Yeah. So the question, it's a good question. So the question is, the grading scheme on the homeworks, basically we give you either 0, half, or full credit. And full credit doesn't mean that you got everything exactly right. It means that your stuff, whether it's math or code, first of all, was readable. So your handwriting is legible, you leave plenty of white space, etc. on you guys are laughing at each other on the written portion. And your code is, it's well commented, you're using indentation, good programming style, and so forth. So that's like a necessary condition. And then we want you, in addition to that, to get close to the right answer. But if you have a small bug in your code and something weird happens, in some edge case, that's that's okay, right? So you can still get full points even if you're not 100% of the way correct. But the question then is, well, if that's the grading scheme, then how do you know if you like really nail the concept and you fully understand it, you got it perfectly right, or if you're just like, most of the way there? And I hadn't really thought about that. That's a good question. So I guess, maybe next semester we will change, or next year in this class, we'll change the grading format to really give you like a percent grade, really carry it through. Yeah, question or suggestion?
So like super close, see me, gave you enough points, but just see me.
Oh, that's a nice
Yeah,
idea.
that's
Yeah.
Because I think kind of the thought that counts grading is nice for a class where it's very open-ended problems and not like a huge amount of resources.
Mhm.
And so, yeah, something like that, where it's just kind of like a comment that's like, looks like you missed something here, come talk to me in office hours, or, ask Nada or whoever.
Yeah, okay, I'm just jotting this down. That's a nice suggestion. And for the folks who didn't hear it online, I think the suggestion is that when we give you guys feedback on the homeworks in Gradescope or whatever, we could jot down a little note that says, see me. So even if you get full credits on something, you'll know that you should still clarify something about the answer. Okay, so I want to continue discussion like this, but I think let's wrap up the lecture material first, and then I can stop the recording, and then we can just kind of do an informal chat. Okay, so the last 2 lectures, we have been talking about modeling the thermal dynamics of buildings. More or less, that means how do the temperatures inside, the rooms and the walls and stuff like that evolve as a function of what we're doing with the heating and cooling equipment and what's happening with the weather. And so we talked about first order thermal circuits in quite a lot of detail in the first lecture. And then this lecture, the second one on buildings, we talked about higher order models of buildings. And we also talked about ways to simulate buildings. So in particular, we need a way when we're simulating the thermal behavior of a building to figure out what is happening with the heating or cooling equipment, which is really influential on the temperature dynamics. So we talked about 2 ways. One, kind of an assumption that you perfectly track the desired temperature set point that you might see on a thermostat, and then another what's called thermostatic control, or sometimes known as bang-bang control, or a type of bang-bang control, where you turn the heater all the way off or all the way on, depending on measurements of the indoor temperature. So, and I think the homework that you guys will work on for next week, basically one problem on that homework will implement, I think, both of those control strategies in simulation. Okay, so then today we're going to talk about this analogy between buildings and batteries, or thermal batteries, if you like. So we'll talk about ways to view sort of the indoor air as a thermal battery, and then the thermal mass, the construction materials, the furniture, things like that, as kind of a thermal battery as well. And this ties into a broader theme. Actually, it turns out that many of the DERs that we study will be pretty well modeled with first order linear differential equations, which, if you kind of rearrange variables and make some new definitions, can be cast as energy storage type equations. So it turns out that model is actually very general. And so kind of toward the end of this unit, in that wrap up lecture for the modeling unit, we will talk about kind of all the ways that all the different DERs, with a couple of exceptions, can really be viewed as batteries. And then when we move into the next unit, more on optimization and control of DERs, we can work mainly with that battery model, with the understanding that it not only represents, say, an EV battery or a stationary battery, but it could represent a water heater or a building or other types of DERs. Does this make sense? Okay, so let's dive into that. So just a refresher, one model, a simple model of a battery that we laid out. We've looked at this a few times now in a few different lectures. But it has a state, call it X, which is the chemical energy stored in the battery. And then the dynamics of the stored energy have two terms in them. One is related to the self-dissipation of the battery. So if there's no energy stored in the battery, then X is equal to 0, and there's nothing here. So there's no energy to self-dissipate. Conversely, if the battery is all the way full, then this X will be large, and this term here will also be pretty large, meaning we lose a significant amount of energy if we kind of just don't charge at all and leave the thing sitting there. And then the other component that drives the changes in the stored energy is just the charging power. And here we're working with the chemical charging power, and we talked about how the chemical power and the electrical power that we exchange with the grid are related. So that is our dynamics. And then we have two constraints. One is on the stored energy. So very often this lower limit here will just take to be 0. But you could say we don't want to drop below 40% charge or something like that in a home battery so that we maintain some buffer of energy in case there's a power outage, for example. So there's a minimum energy and a maximum energy. This is basically just how big the battery is. And then the chemical charging power also has limits. And these could be related to how quickly we can do the chemical reactions in the battery, or they could be related to how much electrical power we can send to the battery. There may only be a certain limit of power or of current that we can send through the wiring that attaches to the battery. So anyway, we have upper and lower constraints on the chemical charging power. So the outline of the next, 10 slides is that we are going to show how the temperature dynamics of either the air or the thermal mass of a building can be put into this basic form. And so that makes the analogy explicit between the battery and the heat storage. So we'll start with the indoor air. And we talked about, for our 2R, 2C model, we talked about kind of the two timing approach or timescale separation, where you can view the thermal mass temperature as roughly constant when you're looking at kind of fast timescale evolution of the indoor air temperature. And then conversely, when you're looking at longer and slower timescales, you can assume kind of a quasi-steady state model for the indoor air temperature, which says that it changes kind of instantaneously. So under either one of those assumptions, you get a kind of a 1R, 1C model. And this is what we get from the fast time scale. This is the same equation that we had from the 1R, 1C, the first model of the thermal circuit that I introduced. But it's also the equation that we got from the higher order models that sort of reduce to 1R, 1C by defining an effective boundary temperature theta and an effective thermal resistance R. Okay, so this is all review. I'm just repeating things that I've said previously. So anyway, here's our governing equation. So then let's assume, or let's define a nominal profile of both the indoor temperature T and the thermal power, or the amount of heat or cooling that we're supplying from mechanical equipment. So we put hats on those. And we suppose that they're kind of consistent with one another. So if we put hats on everything in this equation, in other words, the dynamics hold. So the differential equation is satisfied. So if we look at the rate of change of T hat, this nominal temperature trajectory, it satisfies the right-hand side. It's always equal to the right-hand side of this equation with the nominal controlled power in there. Okay, so then with these two definitions, we can define the energy stored in the internal, so the air inside of a building. So that is just equal to the thermal capacitance C. So this thing would have units of, say, kilowatt hours per degree Celsius, times the deviation of the actual temperature T, the true temperature measurement, from this nominal trajectory, which we denote with the hat. So we could think of T hat here as just the user specified temperature set point, just whatever the wall thermostat reads. Okay, so if we define the energy in this way, then you can show basically by comparing these two differential equations, one for T and the other for T hat. If you just basically subtract the second equation from the first equation, you get the dynamics of the stored energy X. So by definition, c is a constant. So if we take the time derivative of x, we just have the difference of the time derivatives of the t and the t hat. And then a bunch of things drop out when we do the subtraction of the right-hand sides of the differential equations. So the theta terms show up in both equations, so those drop out. And then the QE, this is the internal heat gains from bodies and sunlight and whatnot. That term also shows up on the right-hand side of both equations, so that one drops as well. So we have just a t hat minus t divided by r here, and then QC minus the QC hat. And then we just recognize, well, t hat minus t, that's related to x. If we have a negative sign in there and divide by c, that basically just gives us x. So we get negative x here divided by rc. And the c comes from the relationship, basically this definition up here. And then we can identify that this looks like a battery equation. So we have the time derivative of the energy on the left-hand side. On the right-hand side, we have the energy divided by a thing rc. And we identify that with the self-dissipation time constant tau. And in fact, if you look at the units of R and the units of C, it ends up having the product RC has units of time. So here C would be, say, kilowatt hours per degree, and R would be degrees per kW. So the kW and the degrees cancel, and we're left just with hours from C here. Yes, question.
Sorry, why we define nominal gain?
Up here, why did we define these? So the reason is basically so that we can draw an analogy to battery storage. And I'll show an illustration in a sec of what this would look like to make it slightly more concrete. But let me just wrap up here. So if we're identifying terms in this equation with the battery equation, we have energy, we have the self-dissipation time constant, and then this thing, the remaining additive thing, we identify with the charging power. And rather than a chemical charging power here, we're talking about thermal energy storage. So we identify this with a thermal charging power. Okay. So what does this say? So how to interpret this physically? So suppose that T hat is just a constant and it's just whatever we want. It's 72 Fahrenheit or something like this. Where does that T hat come from?
Yeah, is that our set point? Is that like the typical temperatures we experience and or we would expect in the, where they're coming from?
Yeah, so I would think of T hat. So the question is, where does it come from? So I would think of T hat as kind of the normal operation of the building. So this I guess would just be the temperature that the people in the building want. So it would be kind of the setting on the thermostat, for example. And then we store energy in the indoor air by basically heating it up above that. So if we raise the air by a degree or 2 degrees above kind of what people want, you can think of that as charging a thermal battery, as adding heat to a heat storage, which is the air. And then we could bring it back down once the actual temperature drops back down to the T hat. Then we would say our battery has 0 charge. You could even bring it below, and you could imagine storing cooling basically. Yes.
If T of T is equal to T hat of T, then thermal energy turns out to be 0. Why? Like, how does that happen? Is that like the thermal energy to heat the building to the temperature it's already at is 0? Is that what that's saying? Like if you set
Yeah.
temperature to 72 and it's 72 degrees outside or already inside.
Then you say the battery is empty. There is no energy stored.
So
yeah.
Inside of the C or multiplied by the C term is the difference in like temperature to set temperature.
Right. Right. So there are other ways that we could define the energy here. And actually a nice and maybe better way would be, rather than saying T minus T hat, rather than having kind of a nominal temperature, we could have a maximum and a minimum kind of allowable temperature. So we could say, yeah, people want 72, but really you could drop it to 70 or raise it to 74 and people wouldn't probably notice or care very much. And so then that 4-degree band would essentially define the energy capacity of the battery, if that makes sense. Yes.
Whenever you said that the equation works out for if you plug in all the hats,
Yeah.
does that mean that like the heat input to the system and the heat input from like exogenous loads and everything, that's all perfectly balanced in order to maintain this set point or this critical temperature? And then we're inputting, okay, what if there's noise in the system? What if it's outside those bounds? How does that change in the way that energy is stored? Or,
Yeah, so I guess rather than trying to paraphrase the question, let me just try to explain this again. So the T hat and the Q hat here are defined so that they're kind of consistent with one another. So if the temperature inside the room exactly follows the profile T hat, then we know that under the boundary conditions theta and QE, right? Then we know that exactly the amount of heat that would be supplied by the heating system would be this Q hat. Yes.
Do we not know that already in the first, like the top equation, or are you just saying that T hat and QC hat are like set? Is that the idea of making them nominal?
Yeah.
Because if the equation is like, equal, right, why do we add the hat terms?
Why do we add the hat terms? Yeah, so I guess you could think of these as being set, sort of
Okay.
predetermined. So imagine that you had a weather forecast. So that gave you the theta, say.
Sure, yeah,
And you also had, sunlight forecast and stuff. So that gave you the QE.
okay,
Then everything that shows up in this equation would be sort of predefined.
yes,
And you could calculate a number for T hat at every
Okay.
time, and you would have a consistent number Q hat at every time. And those profiles would be such that this differential equation is always satisfied.
okay,
And then we're thinking that, well, the real T, the true T up here, maybe it deviates from that T hat in some way. We're a little hotter at sometimes, a little colder at other times. And then the real QC would also deviate then from this Q hat, the nominal T hat. So there's a move that I'm doing here, which is called defining a perturbation system.
okay,
So you define some nominal operating point, and then you kind of look only at sort of wiggles away from that operating point. And that's a super common move in control systems, in when you're linearizing systems about some operating point, things like that. So yeah, so as you take 365, 375, probably you'll see stuff like this again in linearization sections. Yes.
The nominal is that. Usually you said the nominal is the actual room temperature of the people that is inside the building, something like that. And the fast time scale, that means you are saying that it's a real time thing.
Okay, so here fast time scale denotes I'm going back, referring back to the two time scale or the time scale separation material that I talked about. So if you have a second order or a higher order model, often some things change quickly, like air temperatures, and some things change slowly, like the temperatures of furniture and cinder blocks and stuff like that. So there's going to be a second model that has to do with the slow time scale. And this model here has to do with the fast time scale. So this here is not super relevant. So here, nominal means, I guess you can think of it as like the set point, the normal behavior of the building. If we're not perturbing or adjusting the behavior of the building for some other purposes, right? It's just if you leave the building under its kind of default operation, what happens? So that's what the hats denote. And then up here, this you can think of as the real measurement, the actual indoor temperature, T. And then the real measurement of the energy supplied to the space, the heat, QC. So the idea is we have kind of a normal building doing its normal thing, and then we're going to do something clever. We're going to, maybe energy prices are low overnight and high during the day. So we're going to preheat the building overnight when energy is cheap. So then we will knock the system away from its nominal operating point. So we will use more energy overnight so that we can use less energy during the day, if that makes sense. All right, thank you for those questions. And this is part of why I wanted to slow down, is because I feel like you guys often have questions like this, and often I'm just going so quickly that I feel like there's no time for it. So that's good. Okay, so here's an example of what this could look like. And maybe I should have led with this because I feel like it would have resolved some of your questions. Okay. So here I'm plotting basically temperature on the y-axis, not shown, and then time on the x-axis here. And here's night, and here's day. You could think of this, I don't know, maybe an office building or something like that. We want the office building to be toasty warm when people are in during the winter, say, and then overnight we're maybe let it drift a little bit. So this would be the nominal set point. It'd be on a schedule. So maybe it's 68 overnight, and then it jumps to 72 Fahrenheit during the day. And then we imagine that there's a band of kind of allowable temperatures. So during the day, this might be, say, plus or minus 1 degree Fahrenheit. So you might say, yeah, people want 72, but is anyone going to notice if it's 71 or 73? Probably not. So kind of anywhere in there, if the temperature is in there, it's sort of fine. And then that band might be bigger overnight, potentially, right? So if nobody's in the building, well, it probably doesn't matter if you let the temperature swing by 2 degrees or 3 degrees. You don't want it to get too cold, so pipes freeze or something like that, but otherwise you might have more flexibility. So then this is the T hat, it's kind of this nominal pre-planned thing. And then this, what I've drawn here, is just one example of what the temperature profile T might look like. So, so suppose, just move this here. These are meant to connect up. So at the end of the day, we drop the temperature set point. Maybe it's really cold outside, and so pretty quickly the temperature in the building drops. And then eventually it bottoms out here, maybe at the coldest acceptable temperature. And maybe we hold it there for a while, and then we begin to warm the building back up in anticipation of this step change here. And then maybe we overheat the building for a while. I don't know, maybe the electricity price is low at this point, but it's going to get really high here. So then we might be preheating, and then drifting during this period. We bottom out and maintain it here for a while. So you could, basically, you could define X as T minus T hat. Maybe I should have done that and just drawn X explicitly to really make the analogy all the way clear. But so here X would be low, like we have basically no energy stored at this point. Up here we've maxed out, the battery is all the way full. Here we're empty again, and so forth. So does this kind of make it a little more clear? Okay. Note to self, next time present picture before math. Yeah, so that's very perceptive. So so here there actually would be like a weird step change in X. If we plotted X, there would be a jump in the graph. Because we go from having T hat, the nominal thing, at say 68, all the way to T hat at 72 instantaneously. So here, at the end of this, we're at just about, I guess, 0 energy stored in the definition that I gave. And then bang, suddenly the set point jumps, and now you're at, like, I don't know, negative something, negative 10 kilowatt hours or something like that. So it's like someone just extracted a bunch of energy from your battery, and then you have to work really hard to basically fill it back up. Does it make sense? All right, so that basically in the battery model, let me just go back to make that clear. In their battery model, we had one equation, a linear first order differential equation, and then we had 2 constraints. We had an energy constraint and we had a power constraint. So let's go through and just kind of carry this analogy along and see what the energy and the power constraints are for the thermal battery associated with the indoor air. Okay, so so again, suppose we have some comfort constraints, and these would just be the bounds, the band basically that was in the previous graph there. And these might be time varying, again, like maybe we're doing a lower temperature set point overnight, something like that. Then the energy here, which this is just the same definition I put down in the last slide, it has to satisfy these constraints. And you can basically take this equation, subtract T hat everywhere, and then multiply by C everywhere. Because C is positive, you can multiply through the inequalities by C, and the inequality directions stay the same, and the inequalities stay valid. So if we do that, we get an X min and an X max. And interestingly here, they end up being time varying, or potentially time varying, because the set point, the nominal temperature T hat, could be time varying. So we've generalized the battery model slightly. In the true electrochemical battery model, we had constant energy constraints, but here we have time variables. Okay, and then how big is this? The energy storage capacity would just be the difference between the max X and the min X. So for an order of magnitude, say for a typical residential building, maybe a single family home, a couple thousand square feet, we might have C kind of on the order of 2 to 3 kilowatt hours. And the band, maybe plus or minus 1 degree Celsius, roughly plus or minus 2 degrees Fahrenheit. Then if we take those numbers, multiply the 2 degrees C by the 2.5 kilowatt hours per degree, we get an energy capacity of about 5 kilowatt hours. Now note that this is thermal energy that we are storing, not which is distinct from electrochemical energy storage. And I'll show basically in a few slides here ways that we can kind of compare the two. Okay, so that's the energy capacity, and then we can do a similar thing with the power capacity. Typically, a heating and cooling system will have a constraint, usually a linear constraint, a minimum that you can provide. This might be the cooling capacity of something like a heat pump, which is a machine that can provide both cooling and heating. So maybe there'd be a negative number here, negative 5 kW or something would be the max amount of cooling you can provide. When QC is negative, that means we're cooling the space. And then Qmax here would be the largest amount of heating that we can provide. So I don't know, 5 kW, something like that. All right, and then our definition of the thermal power, just by identifying terms in the battery model, was just QC minus the nominal Q hat C. So if we subtract a Q hat everywhere in this inequality, then we get in the middle QC minus Q hat, and that's just our P therm. And then we have these terms on the left and the right-hand side. And those define basically our power capacities for charging and discharging the battery. And again, we can plug in kind of typical numbers. If you look at the delta here, say just for a heating system where Q min C might be about 0, we might get kind of on the order of 10 kW. But remember, this is thermal power rather than electrical power, and we'll talk about how we might convert those. But so the basic flavor of the indoor air battery is that it has pretty small energy capacity. So a Tesla Powerwall, for example, I think has about 13 kilowatt hours of energy storage. So it's like 2.5 of what we get from all the air and the sort of shallow thermal mass inside of a house. But the power capacity is actually pretty high. So again, comparing to a Tesla Powerwall, they might be able to charge or discharge that battery at about 5 kW. Okay, so we talked about this sort of fast timescale versus slow timescale thing. So now let's kind of go through that same process, but let's think about the thermal mass rather than thinking about the air inside of a building. So here in the 2R2C model, the governing equation for the mass temperature was very simple. It's just C times the time derivative of the mass temperature equals the temperature difference between the air and the thermal mass divided by the resistance between the two. So you could get more complicated. You could put other terms in here. You could have direct coupling between the thermal mass and the outdoor air. You could have, for example, solar heat directly warming up the thermal mass of the building. But let's keep it simple for now. So then again, we suppose we have kind of a nominal profile, say what the building does during just its everyday unperturbed operations. And we define a T hat, same as it was defined for the air temperature. And let's define the T hat of the thermal mass, basically that satisfies the governing equation under the boundary condition T hat. So playing the same game here. So we have our kind of nominal system, and then we have the actual system, and we define a perturbation system, which is just the difference between the two. So here we define X, same way that we did for the air, take the thermal capacitance, which typically will be about an order of magnitude larger for thermal mass than it would be for air. And then we look at the difference between the mass temperature and the nominal temperature. Okay, so then the derivative of X, just following the exact same steps here, is just take the derivative of both sides of this equation. C is a constant. The derivative is a linear operator, so it separates between the mass and the nominal mass temperature. And then we plug in the equations, and a bunch of stuff cancels. Actually, no, we don't get cancellations here. We just plug in the equations, and we get some separate terms here. So we look at the Tm minus T hat here, group those terms and recognize that that is just negative x divided by c. So that's where this negative x over Rm Cm comes from. And then the other term here, T minus T hat, that's unchanged. So we again just identify terms. The thing we're dividing the energy by, well, that ends up being the time constant. And you can again check units and show that this thing would have units of time. And then the additive term that shows up next to it in the equation, well, we just identify that with the charging power. So this basically says if you want to charge the thermal mass of the building, you just raise the indoor temperature kind of above its nominal level, and then heat will bleed from the indoor air into the construction materials, and those will sort of warm up. And that is the way that we basically charge that thermal battery. Okay, so then we can do the same calculations on the energy and the power capacities. So here are the limits on the temperature limits on the thermal mass are not quite so clearly defined. Like it makes sense to be like, yeah, there are limits on the indoor temperature because that's what determines how comfortable or uncomfortable people are. And you can kind of get a sense for what those should be. But actually, it would be pretty reasonable to just take the indoor temperatures and plug them in as the temperature limits for the thermal mass as well. Because in the model that we have here, basically the only way you can charge the thermal mass is by raising the indoor air temperature. So the warmest you could ever get it basically is the warmest you're allowed to bring the indoor air. That makes sense. Okay, anyway, we play the same game and we find capacity definitions for the energy capacities, basically the constraints here. And then we can plug in numbers. The C for the thermal mass is typically, again, about an order of magnitude larger than it would be for the indoor air. So for a typical house, we might find about 25 kilowatt hours per degree of thermal capacitance in the mass. Sorry, yeah. And then again, we might have about, say, 2 degrees C of flexibility in its temperature. You multiply those and you get about 50 kilowatt hours. So this again is about an order of magnitude bigger than the energy storage capacity from the air. We can do the same on the power. So actually the indoor temperature, the way that we charge the thermal mass is by warming up the indoor air. We charge it indirectly. So then the constraints on the air temperature basically provide constraints on the power that we can charge with. So here is our definition of the thermal power. It's just a delta T divided by R. We have limits here, so subtract off a T hat everywhere in this chain of inequalities, and then divide through by R, which is positive, so the inequalities are not affected. And we get the discharging and the charging power capacities for our second heat battery. Yeah.
For charging thermal mass, do you ever have to worry about like an efficiency term? Like if there were no people in this building and you wanted to keep the cinder blocks up and you try to heat the air, would some of the heat leak out? Like do you have to factor that in at all?
So the question for folks online is, what about losses to the heat that's stored in the thermal mass? So if we wanted to heat up, say, all the concrete in this building overnight because energy was cheap, and then use it during the day, presumably some of that heat would like bleed out over time. You'd lose some. So in the 2R2C model that I'm kind of working from here, those effects don't show up because there's no direct coupling between the thermal mass and the outdoor air.
Okay, yeah.
So the idea here is that over time we could heat up the thermal mass, and then what might happen, I guess, is some of that stored heat would bleed back into the air, and then we'd warm up the indoor air. And
So
then,
with that, if you were to change to a different model, would you want to add more resistors, more capacitors to model?
yeah, so if we wanted to model that sort of direct coupling between the thermal mass, so suppose we cared about the thermal mass in that wall, which is an exterior wall,
Yeah.
then we would probably assign another resistance between that mass and the outdoor air. And that would represent sort of direct heat transfer with the outside.
Okay.
And you could do that, and you could follow through the same steps that we've done in the slides. Okay, so then if we run the numbers, just guessing kind of a ballpark value of the R and the T limits here, we get about 4 kilowatts of charging power capacity, charging and or discharging. So the indoor air had this like small energy capacity, but big power capacity if it's a battery. And then the thermal mass was the opposite. So it has a big energy capacity, but it's kind of hard and slow to charge. So low power capacity. All right, so just to summarize here, working from a 2R2C model, and I guess you can do similar games with higher order models. You can view it as two thermal batteries. So there's kind of a fast battery and a slow battery, or an air battery and a mass battery, if you like. And the indoor air, and then whatever shallow thermal mass is kind of tightly coupled to the indoor air, is a battery with a self-dissipation time constant RC. Its capacity is just C times this delta T, where the delta comes from kind of the highest and the lowest acceptable or comfortable temperatures. And then we have a charging power capacity and a discharging power capacity. And these are defined relative to kind of the nominal power consumption under sort of normal operations. And then the deeper thermal mass, similar. Again, we have an RC time constant, but the R comes from the strength of coupling between the indoor air and the thermal mass. And the C here is associated with all the material that makes up the thermal mass. And then the energy and the charging and discharging power capacities are defined like this. So I think that's kind of cool. So if we just look back at the numbers, like here, 50 kilowatt hour battery. So sort of every house in Lafayette sort of is a 50 kilowatt hour thermal battery. And that's kind of interesting, right? So again, a Tesla Powerwall, call it 10-ish kilowatt hours. This is somehow saying every house has the equivalent of like 10 or 5 Tesla Powerwalls sort of built into it. And it is cool, but it's a little bit exaggerating the effect here because storing heat is sort of fundamentally different from storing electricity. Electricity is like high quality energy. You can do a lot of useful things with it. Heat, especially lower temperature heat like we're talking about here, is not as useful. So we'll talk about ways that you might compare heat storage versus electrochemical or battery storage. So just as a reminder, forgetting about charging and discharging efficiencies for now, a battery, it takes in, say, 1 kilowatt hour of electrical energy. You store it and then discharge it later. You'd get back roughly a kilowatt hour of electrical energy. So you store electric, you get back electric. A heat pump, again, we will talk about HVAC systems and heat pumps in particular next lecture, but a heat pump is basically just a machine that uses electricity to move heat from a cold place to a hot place. So you can use a heat pump to provide heating, space heating, water heating, or you can turn it around and you can use it to provide air conditioning. Anyway, so if we take 1 kilowatt hour electric and we run it through a heat pump, it can typically produce kind of around 3 kilowatt hours of thermal energy, of heat transfer. Now, this ratio, 3 to 1, is called the coefficient of performance of the heat pump. So a more efficient heat pump might do 4 kilowatt hours thermal. A less efficient one might only produce 2. And we'll talk about this much more next lecture. But so this gives us kind of a rough equivalence between, or sort of the value of storing heat, at least for heating applications, versus the value of storing electricity. So here is a battery storage system. So we pull a kilowatt hour from the power grid, we store it as chemical potential energy, later we discharge it, and you could imagine using that energy to run a heat pump, and you would get out about 3 kilowatt hours of heat. And then conversely, suppose we're storing heat. Well, here maybe we would pull that same 1 kilowatt hour from the power grid and run it through the heat pump, produce about 3 kilowatt hours of heat, which we would then store. And we'd extract, again, forgetting efficiency losses and things like that, we'd extract about that same 3 kilowatt hours later to use for heating. So you can see both of these systems are taking in the same 1 kilowatt hour from the grid and producing the same roughly 3 kilowatt hours of heat. But here we are only storing 1 unit in the battery. And down here we are storing 3 units in the heat battery. Okay. So this tells us that storing heat, at least for this like heating application, is roughly, so 1 unit of heat storage is worth about 1/3 of a unit, about 0.3 units of electrochemical energy storage. And then depending on the efficiency of the heat pump, actually that could get worse. If your heat pump is super efficient and you have 4 units, then a unit of heat storage is only worth about 1/4 of a unit of electrochemical storage. Arash, you had a question?
What kind thermal storage you're referring to?
So what type of thermal storage are we referring to here? Yeah, it's sort of generic. So here I've made it kind of abstract, but we could think of it as the passive thermal storage, as you put it, which is kind of the, you know, the stuff you get for free from just the air and the thermal mass of a building. 2 lectures from now, I guess on next week, Thursday, we will talk about active thermal energy storage systems. And so, you know, maybe you're making some water hot to use for heating later, something like that, or freezing ice to use for cooling later. And so this also basically works for those types of systems. Yes.
What's the self-dissipation of the battery versus the thermal storage? Because that might affect this. So
Yeah. Again, we'll talk about thermal storage next week, but the question is, what is the self-dissipation of the thermal storage? And it basically has to do with heat losses. So suppose that we were storing heat in a big water tank inside this room. So then the self-dissipation of the energy stored of the water tank, viewed as thermal storage, would just be basically conduction through the tank wall to warm up the ambient air around it. And water heaters, they do bleed a little bit of heat. You know, if it's in a cold basement, it'll lose a little bit of heat over time. But the more insulated the tank is, the less that effect is.
but the batteries will stay in like the equation that we talked about, it should be 0.15 to 0.4 in most cases, the range.
I think that 0.15 to 0.4 that you mentioned was for the energy intensity of driving an electric vehicle. So that'd be like kilowatt hours per kilometer driven. So that's a separate effect. But there is self-dissipation in a battery as well. So you've probably observed this with your phone or your laptop. If you know you go away for a weekend and you leave your laptop, it's fully charged, but it's unplugged. You come back 3 days later, you might find you have 95 or 90% battery. Right? So there is some self-dissipation associated with chemical storage too. Yes.
For battery is like significantly larger than that of an electrical battery.
So the question is, would the time constant for a thermal battery be significantly larger than it would be for an electrochemical battery? And I think the self-dissipation time constant. So for like a watt for what Arash called active thermal energy storage, like you know, a water heater or an ice storage system for commercial air conditioning, something like that. I think the time constants are fairly comparable between those systems and batteries. But for the kind of passive stuff that we're talking about here, so for the air, for example, the self-dissipation time constant is RC. R might be on the order of 2 to 3. C might also be kind of on that same order. So this product here might be around, you know, 5, 6, something like that, hours. And for a lithium-ion battery, we talked about it might be like 1,000 hours. So there's like a couple of orders of magnitude difference. So that tells you that this is sort of a lossy battery, right? Like you preheat the air in this room, and pretty soon that heat is going to dissipate, either by bleeding out outside or by warming up the thermal mass. Does that make sense? Okay, yes.
So just sort of off of that, is there ever if you are using electric heat pumps and, you know, maybe one that can work both ways, is there ever a benefit to storing energy as, you know, thermal, and whether it be in, you know, thermal mass or in shallow mass or the air, when you can just keep it in the battery?
So the question is, suppose you're using a heat pump, and maybe a heat pump that you can reverse the cycle and provide cooling, but you're using it maybe for like a space heating application. Electric heat pump. So would there ever be value in doing thermal storage for that application as opposed to doing electrical
Yes.
storage?
Even if it were, you know, ice for HVAC or something, if you could just run a heat pump to take heat out, does it ever make sense to make ice?
So yeah, so the answer is maybe, or it depends, right? So one of my grad students is working on this problem. And it really depends on the application. It depends on the prices of things. So you can imagine, like here I said that a kilowatt hour of thermal storage is only worth 0.3 kilowatt hours of storage in a battery. But what if the thermal storage is dirt cheap, right? Like what if it's just a big oil drum full of sand or something like that, or just a big tank of water? Then you still might say, well, you know, rather than buying an expensive battery, I'll just buy, you know, some dirt cheap heat storage.
Yeah, because then you can just put electricity into the thermal energy. Okay, that makes sense.
I mean, you have to think about how do you recover that energy
Yes.
in a useful way,
Yeah.
right? So yeah, just heating up a drum of sand is like not that interesting unless you can somehow get the heat back to warm up the space. But yeah, exactly. So yeah, it has to do with the costs of the energy storage. Another consideration here that's sort of interesting. Well, I guess it's not really illustrated here, but there can be advantages in being able to downsize the heat pump. So if you are able to run both the heat pump and discharge the thermal storage at the same time. So suppose on a really cold night, you have heated up a bunch of hot water. And suppose at that night, you can run the heat pump kind of at capacity. And maybe it's too small to by itself keep the building warm. But then you can also discharge heat from that stored hot water. Run a pipe through an air duct and have a fan to blow air over it, something like that. Then you can kind of get away with a smaller heat pump because you have a secondary heating source in the basement. So you can save on basically the upfront cost of the system. But yeah, it's a complicated question, and this is like why PhDs can write papers about it.
I've seen a video of, there's a company in Sweden trying that, where they heated sand to like 800 degrees. A big room full of sand, and used it to heat Swedish houses in the winter.
Oh, interesting.
So it was like excess renewable energy when heating sand, heating houses.
So the comment from folks online is that there's a Swedish company that is, actually, if you could find a link to it, that'd be great. There's a Swedish company that is trying this out, basically use excess renewables from solar or wind, something like that, to heat up a bunch of sand, and then later use all that hot sand, presumably run some working fluid through it, and then circulate it around to houses to provide heating. It's a cool idea. And yeah, I mean, thermal storage it's usually fairly simple. People do get very fancy at kind of designing, nano fabricated materials that have just the right melting point, boiling point, whatever it is, just the right thermal properties for energy storage. But it can be done really, really cheaply with stuff like sand and water and bricks, very simple materials. And I'll show you, I guess, next week some pictures of thermal storage systems that are used in the US. Okay, so I think I said I was going to do some discussion. I thought this would take like 20 minutes, and it actually took like an hour. But that's, yeah. But that's perfect. And I would love to be able to do a more leisurely pace in the lectures going forward here. So I think I will stop recording, and then we can just do kind of open discussion as long as people have comments, and then we'll just take off whenever we run out of stuff to talk about.